This is general. This is the construct. So right now your account number is there. Once it gets activated, we can get the claims done.
And maybe for that scholarship application and
Yes, everyone, I think it's now 200 just crossed. I think we can start. Okay, let me share my screen. Okay. I'm sorry. I'm sorry. I'm sorry. I'm sorry. Yeah. Thanks. 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 Right. Right. Okay. Thank you, everyone. Thank you so much. Yeah. See, now there are two ways I can see things. Number one, classical systems, and one is quantum systems. Okay. Right. So the classical systems are the one macroscopic, means large. Okay. And this one is microscopic. Okay. Right. For example, macroscopic example would be a moving projectile. Okay. The example within that example is a moving cricket ball. Okay. Right. So to explain that, to explain the dynamics of that object, okay, we will use Newtonian dynamics or Newtonian laws. Okay. To study the dynamics, we would use Newtonian laws. Okay. We would be using Newtonian laws, which are, first law of Newton, second law of Newton, third law of Newton, and so on. Any other laws defined or described or derived from that. So those comes under same thing. Okay. And how are we doing this is, for an object which is moving, we usually specify, okay, specify the position x and the velocity with which if it is moving. So not simple velocity, I would multiply the velocity and I would get momentum, which is a linear momentum. Why do I want to do? I want to even capture the idea of what is the object mass. If something is moving very tiny, I don't bother. Like a dust speck which is moving, I don't bother. I can't see that. If a projectile is moving, which is important. Okay, right? So, which means I would need position and momentum to represent the object dynamics. Okay, right? So this is a classical mechanics for you. Now, beyond that, I can go further. I can go and find if something is moving, it is moving, I can find kinetic energy, which is equal to half mv square. I can find a potential energy if an object is placed on some height. Let's say my mobile is on the desk. Okay, right? So potential energy would be mass into, okay, mass into gravity into height. It is over the floor, it is about height. Sometimes I find the potential energy negative also. People represent negative energy. What they mean is, with respect to ceiling, you hang something about the length L down, okay, of mass M. So in this case, the potential energy is minus mgl. With respect to reference, it is in the negative direction. That is what the potential energy means. Okay, right? So it's all respect to which reference frame you are taking a potential energy. Fine. Okay. So kinetic energy I know, potential energy I know. I can represent total energy as kinetic energy and potential energy. Okay. And to know the dynamics of this something which is moving, I usually solve. I'll write down first Newton's second law, which is mass into second order derivative of position with respect to time. Okay. So if I solve this differential equation, I would get what is the position of the object in time. I would get. Similarly, I can also find what is the velocity of the object in time. If I know the velocity of the object, I multiply with m, I will get momentum of the object in time also I'll find. Okay, those are the basic things usually I'm worried about the system and would like to know about the system. Okay, so this is a classical physics for you, right? So when I take a simple pendulum of mass m which is moving, if you see a simple pendulum which is making an oscillations, you see one interesting thing, it is would like to stay in a equilibrium position which is at this position where theta is 0. But what you are doing, you are going to give your angle of some theta equal to, let's say, some 50 degrees. Okay, you are displacing its equilibrium by giving an amplitude with an angle specified by 50 degrees. Because of that, what you are creating? You are creating oscillations of that object between the left theta equal to 50 to theta equal to minus 50 degrees. Okay, so you are giving that amplitude for that, and it makes an oscillation. While making an oscillation, see, when it is at the equilibrium point, the kinetic energy is what? Kinetic energy, some value, maximum it will be there. But when it at the extreme point, potential energy is maximum, but kinetic energy is 0. Means it goes and stops there. The kinetic energy becomes, earlier it was increasing in this direction, it stops means kinetic energy becomes 0, then kinetic energy starts picking in the opposite direction. When it comes back to equilibrium point, we even say the potential energy achieved its 0 value, because we will treat potential energy at equilibrium point is 0. Okay, right? So the potential energy becomes 0, then it goes up, the potential energy becomes maximum, kinetic energy becomes 0, then it comes back. Okay, so basically what you see, okay, if you plot the potential energy versus time, if you just plot, so potential energy initially it is 0, increases to maximum when it comes to center, and comes down the negative and then increases. So this is the potential energy for you. So initially it is 0 when I just take it and holding it. When I'm holding it, it's not moving. When I just leave it, this mass goes increasing, potential energy reaches the maximum value, and then increases in the negative direction. So this is the way the equilibrium point. Okay, right? So the kinetic energy I'm drawing. Kinetic energy. So kinetic energy is 0, increases to maximum and then reaches to 0 value, increases in the negative value. At the same time, if you plot I just plotted a kinetic energy. If I plot potential energy, it is exactly opposite. What I mean is, initially I am holding it, it doesn't have a potential energy, so it goes in opposite. I'm sorry, is it okay? Yeah, I think so. Okay. So this is what happens with respect to kinetic energy and potential energy. Okay. At any given point, right, I think probably something like that. Okay. So just keep it aside. This is what we have for classical system. Okay. Now let's talk about quantum system. And why this is all I'm giving, there was a question asked to me. I am fluctuating as it's a deviating or just transferring between classical domain to quantum domain, or classical variable to quantum variables, and whichever way, as if it has my own wish. No, it's not like that. So there is a way to go shift from classical to quantum. When it comes to microscopic system, you see, yes, of course, I can specify position. Of course, I can specify momentum. Remember, are possible, allowed, I would say, are allowed to use to specify the dynamics. Okay, and not only that, there is more. So quantum particles are macroscopic particles, example like electrons. Okay, they may have something called along with position and momentum. They can rotate about some nucleus. They may have rotational angular momentum. Okay, what I mean is they are rotating about the nucleus. You see, okay. Earlier they have just a linear momentum. Since they are rotating about axis center where the nucleus is present, so angular momentum they are going to have, which is r cross p. Okay, they're going to have a angular momentum. That's fine, understood. Okay, and they are existing in the vicinity of all the charges. Okay, all the charges in the sense, see, there is another negative charge around, let's say another electron pushes this electron away from it. There is another positive charge around, attracts this electron towards it. Likewise, there are different charges are around. There are exerting some forces on this system, and those forces, in fact, create some kind of a hole where this electron is stuck. Okay, this electron is stuck in that hole, right, as if it can't go anywhere. It's like a big huge gathering is there. Usually you are stuck inside, so you can't move anywhere because you are dictated by everybody's presence around. So your position to move here and there, it is actually dictated by their surrounding. So this is called potential well. Okay, so electrons surrounded by other charges, okay, right, creates a potential well. A well is something, if somebody falls into well, some animal falls into well, it can't go anywhere, so it is stuck inside. If somebody comes and lifts it out, so likewise a well is created like that. I am just drawing a one-dimensional well, which is x is equal to 0, x equal to n. Now, if I place an electron inside, the electron cannot go anywhere inside because you see, on if it has to go to the left side, it has to climb, and not just any climb. It is an infinite potential, infinite height. Okay, so electron to go to the other side, infinite potential means it has to go up, come out of the hill, and go towards the left side. It can only move in one dimension. You see, okay. Now, this electron potential is created like this. Electron can have angular momentum. The moment it have angular momentum, there is something called, it will possess a spin angular momentum. Let's say I'll give a rotation R. I'll give a hat, angular momentum hat. Okay, electron not just rotating about the nucleus, electron can also rotate about itself, its own axis, just like Earth rotating about its own axis. So there is another spin momentum, which is EMS, due to individual spin. I'll say I. Okay. So you see, I'm coming up with the variables to describe a quantum system or a quantum microscopic object, not only with position and momentum. I am coming with the other internal existing operators or the observables which tells about the system. Okay. Now I need to have a difference between the momentum I did use for a macroscopic object to the microscopic object. Okay, why do I need a difference? Because see, in classical objects, I can exactly measure x and p values. You know why? That's, I can notice them perfectly. But when it comes to quantum object, they are not like that. You know why? the, the moment they become smaller and smaller, they are going to possess a quantum nature, which is a wave kind of a behavior, where the size of the object dictates the wave nature whether to exist or not. So I am going for a smaller and smaller, it is going to become a wave, or it's, sorry, I'm sorry, I should not even say that. It's going to show wave nature. The moment it shows a wave nature, I may have inside the potential well a wave like this, a 2D wave, so standing pattern. Also, it can have a wave like this. Also it can have wave like this. Okay, and I would call this is a wave with the orbit size n equal to 0, orbit number, this is n equal to 1, this is n equal to 2, and so on. These are different wave natures, can exist with different energies. Okay, so electron which I put inside, it becomes, it shows a wave nature. Because of wave nature, you see, I can't send anything through the wall, but I can send my voice through the wall, because voice is a disturbance, is a sound, is a wave which can travel through. Since the electron shows a wave nature, what happens within the, even within the this infinite potential well, it can have a wave nature, even go not only just confined within the, within this, it can also go beyond and then just deviate, decay. Okay, so inside I have a wave nature, but outside it can just decay. You know why it decay? Because of the opposition given by the material. Okay, now see, there is some wave function exist beyond, even in the infinite potential well, even though somebody has not given any energy to the electron, it can even have a wave nature on the other side in the infinite potential location. But the moment I have a non-zero wave function psi, even beyond x is equal to L, let's say x is equal to L plus some delta x. Even in that region also I have some non-zero wave function. Non-zero wave function means if I check its absolute square, which is going to be positive, because it's absolute square. It's going to be positive means what? Electron, see here, probability amplitude square is a presence of the probability, right? The probability of the electron shows electron may also exist in the infinite region. Okay, so the electron can exist in the infinite region even though it is a material, right? So because of this, what people thought, since it's a wave in nature, always I'm going to make a mistake in finding its position, in finding its momentum. I'll always make a mistake because it's wave nature. If something is vibrating, it appears to be like a blur. If a fan is rotating, appears to be like a blur. I can't exactly locate the wing. Same story, electron is kind of a vibration. It appears to be blur for me. So there is always a make a mistake. So Heisenberg uncertainty principle comes into picture where it is more than Planck's constant by 2. Okay, so because of these reasons, you see, I can't have just a specific description. Just like I had a quantum mechanical distribution, classical mechanical distribution, fixed x, fixed p, fixed energy, fixed kinetic energy, fixed potential energy. I can't have that. They are always dynamic in nature. So for that, to represent the difference between the quantum mechanical observables, which represent the dynamics of the quantum system, to classical observables, I will say I'll put them a hat above them. Hat, hat. Okay. The moment I put a hat, what it means is they're quantum mechanical probes. You remember, they're like a thermometer, they're like a barometer. Like what their job is, they go and act on the object and give me the required number. For example, I want to know what is my height. I will put the scale against me, okay, a meter scale, and find out what is my height. So these probes are like that. They go and act on the quantum system and give me what is the exact, the variable, the observable result corresponding to that object. For example, electron is moving, so what is its corresponding position in given time? I take the observable x and measure, act on that observable system. If I something electron is moving, I act a momentum, linear momentum operator on that, and I'll find what is the corresponding momentum numbers. I act angular momentum, electron is rotating about a nucleus, I'll find angular momentum. If electron is having some kinetic energy, so it has some potential energy, together it is going to have some total energy. Now the question is, can I have a kinetic energy, potential energy together? Just like in a classical system, I call that as total energy. Of course not. You know why? It's very much dynamic in a quantum system. There, the total energy notion is not there. It is represented by Hamiltonian. Total energy is represented by Hamiltonian. What is this Hamiltonian? We put a hat on that observable, which is going to be kinetic energy observable hat, potential energy observable hat. By the way, I know kinetic energy usually half mv square. Remember one trick here. Mass of an object is not going to change whether I am talking about quantum system or a classical system. It is going to be same. Okay, right? So classical and quantum systems are the same. The mass is, I don't have a hat on the mass. Does it as a quantum or a, but velocity has a mass. Sorry, velocity has a quantum mass. You know why? It is something derived from the position, varying position. So I will have hat on that. Okay, and kinetic energy is that. Now when it comes to potential energy comes because of what? In a classical system, potential energy comes because of something is placed about some height, something is hanged from some reference point. Okay, so that is the potential energy classically. But when it comes to quantum mechanical, what is the potential? Potential is, it is surrounded by some other charges. It creates a small hole, like a something dug. People usually say you will fall into the hole if you just do, if you go into this kind of a attitude, because once you fall into the hole you can come out. Okay, something like that. The surrounding environment creates a hole where something falls into that hole. It is cannot come out, but only it can show some dynamical behavior in terms of wave nature. You see, literally to pick it out and put it out, maybe you have to do a classical kind of a, you have to hold the electron with some forceps and take it out. Okay, fine, very good. Now you see the kinetic energy is like that. Potential energy, so if it is something or like hanged, something is hanged from the ceiling, I can give a potential energy representation just like I did E minus mgl, mg into l. Okay, if it is something placed on a desk, I can give a energy, but here it is placed inside a potential well. I don't know how to give that potential energy, but there is a trick. What is the trick is, here in classical system, if I have a potential energy in the system, I just disturb the system by some means. What happens? It is going to execute the oscillations. Remember, even though the system is classical, because of the potential energy, which is minus mgl, you see, minus mgl, if I disturb the system with the potential, having some potential energy, if I disturb the system by giving some deviation, it is going to execute the oscillations. What kind of oscillations? The oscillations were yesterday we derived. The oscillations were, okay, I'll tell you, the system is moving with the position variation. This is the mass into acceleration. Let me give. This is going to be equal to the change in the potential energy with respect to position. You know why? Because I'm creating that change in the position, which is du by dx. I don't know what is that U form, but I know that the potential energy changing would act like a force for the creating the oscillations. Okay. Now I will do one more thing. What I will do, since the up, like see, when I try to create an oscillations in the quantum system or a classical system, the system will always oppose you, because it wants to stay in equilibrium. It wants to stay quiet, but you are disturbing it. So what is that? It is just equivalent to a spring system. When I try to stretch, it opposes, and I try to compress the spring system, it opposes. In the same fashion, it is going to oppose with some spring constant K. I don't know what is that spring constant. K multiplied by how much disturbance you are creating. Okay. So this is a classical system for you. Doesn't matter. It also applicable in quantum system. I'll tell you when it will comes to application. Okay. Now we have the equation, a two-dimensional equation. There is a minus sign comes because it always opposes. If I write down this equation into second order differential equation, okay, k by m into x. If you solve this equation, it comes out to be nice sinusoidal solution, which is solution of this equation in time is some constant sine omega x. It's nicely oscillating curve with an amplitude a naught in time. So x of t in time. This is a solution. Now, these oscillations are existing means oscillating with an angular frequency omega, which is square root of a by m. Okay. Now, I want to know what is the spring constant. Spring constant is what? Rigidity of the system. It opposes any action taking place on that. So, whatever is the spring constant is now calculated from the reverse. I do the reverse. I find out the oscillations I can have in that system. From the oscillations, I can find if at all there is an opposition in the system in terms of spring constant, I can represent that as m into omega square. Now you see, m is a mass, doesn't matter, it's a classical or quantum. But omega is something is slightly different. Omega is, it can become quantum in nature. Okay, omega is classical observable, but when it comes to quantum, it becomes. By the way, what is omega? What is omega? It is r cross v, radius about which something is doing oscillations, cross v. R can become a quantum, v can become quantum, so overall omega can become a quantum. So when I move from classical to quantum, what I should do? I should write down the spring constant accordingly. So here in the quantum system, the potential energy, okay, right now, okay, let me continue one more thing here. What is the spring? If the moment I know the spring constant, I can find what is the total potential energy of the system. Okay, the potential energy of the system is half k x square. Okay, how did we get this potential energy expression? We even derived it yesterday. In terms of spring constant, this is there. How? If I have potential energy in the system, if I try to disturb with the position by stretching a spring, so the spring will oppose a restoring force with minus kx, right? Now, okay, so variation is negative, it's opposing, and restoring force is opposing, it's negative. Okay, now what happens? Just a minute. Send, 1 minute. Yeah, right. So if you now take it out, integrate, what you'll get? Half kx square. Potential energy is half kx square. I'm in class. Give it to you. Okay, right? So half kx square, which means the potential energy is half kx square. Even though, remember, if the system even doesn't have a spring, it can oscillate. Means it has a rigidness inside, it has a opposition inside, which can become a spring constant, which can be represented in a spring constant. What is that spring constant? K. If it has an oscillation, if it has a mass, we simply m omega square is a spring constant. Remember. Now you come back to quantum system. Okay, in the quantum system can vibrate, electron can vibrate just like a waves. It can show oscillations. It can show oscillations, even though which is existing in a potential well. It is showing the wave nature. Wave nature means what? The disturbance is traveling. So there is a oscillations in the system. If there is a oscillations in the system which are having some angular frequency omega, the oscillations are with angular frequency omega. The system is having some mass. You just to square it, m omega square, you are going to get a spring constant. Okay, the spring constant of the system. Now, not only that, I want to find what is the kinetic energy, potential energy of the system, even in the quantum, so potential energy of the system, even at the quantum level. So, the potential energy of the system with the hat would be half spring constant x square. Now, I have to add a hat. And now I have to add a hat. So, my potential energy is half m, okay, wait a minute, half m omega square x square. For the omega, I'm supposed to add a hat, but now and then people don't add a hat. So that is immaterial because I'm more concentrating on my position and momentum. That is the most important thing. Now, kinetic energy, half mv square. What I will do? Let me do one trick here. Okay, kinetic energy. Just a minute. Kinetic energy is equal to, okay, multiplied by m divided by m, it becomes p square by 2m. So the overall Hamiltonian of the system is p square by 2m plus half m omega square x square. This is a Hamiltonian for you in terms of total energy. Remember now, I use the concept of oscillations and vibrations which may exist even at the quantum level. It is not the case. I'm not saying I'm using classical analogy to find the total energy of the system. It is not. I'm using the idea of vibrations, using the idea of oscillations to find the total energy of the system, because system can vibrate, system can move. So kinetic energy and potential energy I got. Okay. Now the next thing. Okay. Yeah. So there is a question asked by Lakshmana and Narasimha once again. Can you please confirm once that electron execute vibration and oscillation motion within the atom? Okay, right? You remember within the atom, the electron is doing oscillations. Oscillations means it is making one complete rotation. Okay, this oscillating clocks we have, so there is a bell which is moving, which oscillates. Okay, it's oscillating. Something vibrating means it is oscillating to a very smaller extent. Okay, if you know tuning fork, you people hit tuning fork and you put near to your hair, the ear, what happens? The tuning fork actually vibrating. Those vibrations create a very high frequency which we can't hear. So which if you put close to the ear, it creates a vibration. It goes and hits your eardrum and vibrates the eardrum, or just some kind of wires on the eardrum. That actually creates a noise for us. That is what we hear. Okay. So the oscillation is also a vibration. Rotation is also vibration. Vibration means what? From some stable situation, somebody is creating vibrating. Equilibrium position, somebody is creating vibrating. So remember, yes, electron rotates about the nucleus is some kind of a oscillation. Okay, it may not be left to right. So left to right means what? It starts from a position, goes to the right, come back to that position. Means it is making one complete rotation. Okay, fine. So now the total energy I got as a Hamiltonian. Now in the quantum systems, okay, everything is represented by observables or the operators, which are a position observable, angular momentum, linear momentum observables. Okay, like observable means hat, operator. It's like a tool. Like that, I have a Hamiltonian observable with a hat. Okay. Now, the Hamiltonian of the system is like it is taking things into the picture. It is taking the system and its surrounding and putting the twins together and giving me the entire description. Okay. When I go to very smaller and smaller electron inside an atom level, I can even go and simply represent the information about the system in terms of matrix. What is that matrix? Hamiltonian matrix. How do I do now? Okay. Now I only concentrate. See, the electron can exist in this orbit and this orbit and any other orbit. Okay, how it can exist in any other orbit? The moment I supply the energy, okay, if I supply the energy, it can go to higher orbits. Just a Yeah, I'm sorry. Yes. So now, if the electron is here, to go to the next level, I need to supply a photon of energy. Then it comes here. To go to the next level, I have to supply a photon of energy. It goes to there. So the amount of energy I supply, that much is a chance that electron goes anywhere. Okay, this is just a semi-classical picture they call. I take some part of classicalness to understand, some part of quantumness to understand. I put them together and understand it here, because I can't go pure quantum, I can't go pure classical because it's a tiny thing. Okay, now I confine my system of electron to only two levels. What it becomes a ground level and excited level. Whether the electron only to exist in the ground or in the excited was dictated by amount of energy I am going to supply. So I can supply energy in terms of photon. Also, I can supply in terms of some electric field. I can take a plate of positive charge and negative charge. I can put. Now, what happens? There is a positive charge on the above, negative charge on the bottom. So, electron may jump to the excited charge, excited level because of the attraction from the positive plate. Let's say I have created an electric field E. Okay, now please see the E I am using for electric field representation, not for the energy. So just to have, let me say EL, electric field. Now, okay, now the electron is going away from the nucleus, means what? If the atom is there, nucleus is there, electron is going away. So electron might go away and it can create a positive charge and negative charge cloud like that, going away. So going away, it creates a dipole. A dipole is created. Okay. So what is the dipole? Dipole is some charge, let's say hydrogen atom, only one electron is there, one positive charge is there, proton. So which are separated by Q into some distance. Okay. So that is that, sorry, Q into some distance. Okay, not a D. I'll write some 2 into L. L is just from center, the positive charge distance. From the negative charge, another L, so it's a 2L. Okay. So this is equal to dipole moment of the charge or the system. Now, this dipole moment is created because of the electric field. Okay, this dipole moment has a direction. It is only moving in a particular direction in parallel to the electric field. See, electric field actually creating a dipole moment. Now, the interaction between dipole moment and electric field, I'll write as D dot E, dot product between electric field and the dipole. Okay, so D dot E dictates whether I need to have electron going away from the nucleus or close to the nucleus. In fact, it creates an oscillation if my electric field is also oscillating with some omega frequency. So dipole also makes an oscillation, going away, coming back, going away, coming back. So in this way, now the electron is sometime in the ground state, sometime in the excited state. Now I can write the total Hamiltonian of the system as, okay, electron exists in the ground state with some energy omega 0, h omega. It exists in the excited state with omega 1, and also it oscillates between these two with the D dot E cos omega. Now omega is omega 1 minus omega naught into T, and this is the complex conjugate of this quantity. Whatever is this quantity is there, and that quantity will come with a, let's say this is some mu into A, so mu into E star. So this is the total Hamiltonian for you, represented in terms of matrix, okay, where I'm only talking about two states of the system. Now I represent it in terms of a matrix. You see, this has energy of the system and the interaction with the surrounding, but this may not be exactly explicitly written as kinetic energy, but total potential. I may not be written like that, but I did take into consideration the motion of the electron away from the nucleus in terms of total energy. What the energy is going, existing in the ground state with energy, or going into the higher state to the energy by adding an extra because of the electric field. So now I have a Hamiltonian for you in terms of 2 by 2 matrix. Okay, so you see, this is the pure quantum system, pure quantum representation, pure quantum, pure representation. Okay, and there is an electric field is not fixed, it is varying. See, for quantum everything is quantized, but electric field I am taking varying, so it is again a part of classical thing is coming, it's called semi-classical. Okay, now overall Hamiltonian is pure Hamiltonian representation. Pure Hamiltonian is represented using some classical, but energies of the system is pure quantum. It can be here or there, quantized energy levels. Okay, now you see, I am using the representation of expression for the Hamiltonian, a representation of matrix for the Hamiltonian. Now, if I am able to exactly know the position of the electron, moving of the electron, its kinetic energy around the electron, if I know, what I'll do, I take the Hamiltonian in the expression form earlier, whatever I derived, I multiply that Hamiltonian onto the quantum state, in position and time quantum state, and I will solve the Schrodinger equation in terms of eigenvalue equation. Okay, so the eigenvalue equation is common. Hamiltonian can take kinetic energy plus potential energy expression form, or if it takes a Hamiltonian matrix form, in the matrix form what happens, okay, in the matrix form what happens, so E is now energy, it's not an electric field, okay, En is energy, E takes at a operator IH cross dou by dou T. Okay, so somewhere the other way I need to bring the dynamical thing. So H is a matrix. How do I know the dynamics of the system in time? So I need to convert energy into a time domain derivative. So when I do this, you know what happens. See, you see, this is how you usually need to understand. H psi is equal to IH cross dou by dou T psi. I'll not specifically say psi of r or anything. Now you see, this is a differential equation in time. You send the time to the left, psi to the right. What you get? Dou psi by psi is equal to minus I by h cross dou t and h into dou t. Now you can integrate. Okay, when you integrate, I'll get a log of psi with some limits. On the right, I have minus I by h cross. Let's time being, you remember, see, I don't see any time dependence. For example, let's say d dot e is not oscillating, just a fixed value. So let's say in that case, h is in like not a function of time. So they call it independent of time. So h can come out. So I'll have multiply integration of dot t. I'll get a t. Now let's say some 0 to some time t integrating. So what I'll get? Ln of psi of t minus, okay, ln of psi of 0 I'll get. On the right I'll have minus I h cross h into t I'll get. Okay. Now send the log to the right side. I'll get psi of t is equal to exponential minus I by h cross h of t multiplied by psi of 0. What is this? This is quantum system in time evolving from time 0 to t by unitary operator. What is that unitary operator? Unitary operator is simply exponential minus I by h cross Hamiltonian into t. This is a unitary operator. Okay, all the quantum gates are unity operator or a matrices because my Hamiltonian was represented in terms of matrices. Hamiltonian is taking into the surrounding. For example, Hadamard gate. What is the unitary operator for the Hadamard gate? Hadamard gate unitary operator is just a Hadamard gate. Okay, let me have Hadamard gate as it is. Hadamard gate is 1 by square root of 2, 1, 1, 1 minus 1. This is Hadamard gate. Now question is, what is the corresponding Hamiltonian? Corresponding Hamiltonian. What is that? You can find in a reverse fashion. How? You equate unitary operator to the existing matrix and you do the inverse. For a given time, you can get a Hamiltonian corresponding to Hadamard gate. You would get something you would get. You can do, you take a log on in the entire equation. Okay, it becomes a log of matrix. On the right hand side, I'll give you exactly hint. Minus IH cross H Hadamard Hamiltonian is equal to log natural logarithm of 1 by square root of 2 matrix 1 1 1 minus 1. Okay, I want to find Hadamard matrix Hamiltonian, which would be, okay, IH cross, okay, divided by time log of 1 by square root of 2 1 1 1 minus 1. Okay, so this is the Hamiltonian corresponded to Hadamard gate. Hadamard gate, what it does? Hadamard gate comes and act on 0, pushes to quantum system into superposition. Means Hadamard gate is like a pulse, comes to the electron, push the electron back and forth between 0 and 1. So that Hamiltonian corresponding to that photon pulse is this. Okay. Now, depending on the situation, I have to take the description. When I am only talking at a very tiny level, an electron being oscillating between 0 and 1 with a pulse, I will use the Hamiltonian description. I'm only confining to that small inside location. See, small inside location, inside, small part. Or if I have an electron inside an entire crystal, okay, it is inside a crystal. Let's say the NV center, a diamond they will call. Inside a diamond, there is a nitrogen vacancy center you can create. It is surrounded by everywhere. Now I can't have this kind of a description. There I have to bring in the entire kinetic energy description of the system and the entire potential energy around. Everything I have to bring. I have to solve the Schrodinger equation. How? I have to solve the Schrodinger equation by using p square by 2m plus potential energy, which is position, multiplied by quantum system is equal to E multiplied to the quantum system. This entire equation I have to solve. Now, yesterday we tried to solve it. When we tried to solve it, we found it there is a second order derivative here. Second order derivative in space. P square is minus IH, sorry, not IH, just h square in one dimension. I am writing h square dou by dou x square by 2m. This is the second order derivative. I can't solve it. What I do? I'll go apply a trick. I'll introduce from capital P to small p by scaling. P is a Hermitian operator and small p is also a Hermitian operator. I get rid of this m and omega, all those things by scaling. Let's say divide by m omega h cross. Okay. I want to get rid of that h square on the top. So I'll do that. The moment if I do, the Hamiltonian becomes, okay, 1 by 2, I think, p square plus q square and I think h omega, something like that. Okay, if I remember correctly. Okay, if you want, I can exactly write down looking at my notes. Give me a second. Okay, p square plus q square. Exactly perfect. Now I have a p square and q square. I have quadratic terms. Quadratic terms are always dangerous things. You know why? If I have an equation between x plus y, it's a linear term. For every given x, I have a given value, single linear. But if I have an equation like y equal to x square, for given x, I have two values. You know, for a given x, I can get, for a given y value, I have two x values. See, there is a minus x1 and minus plus x1 satisfies same y value. So it's a quadratic. So people want to avoid. So just to avoid a quadratic value, what I will do, I'll introduce p and q in terms of a non-Hermitian operator A, which is p square, okay, Hermitian operator, which is not a p square. A is q plus ip divided by square root of 2. And A dagger is just a complex conjugate of that quantity. So if you introduce this non-Hermitian operators, Hamiltonian becomes much simpler. What it will become? It will simply become h omega A dagger into A plus 1 divided by, sorry, plus half. Now I have just a linear terms. How? I convert my A dagger A into number operator, which tells me in given system how many number of particles are there. N represents number of particles. Okay. So let's to confirm or conclude the question. Why did I move from Hamiltonian from expression form to Hamiltonian matrix form? Why did I move energy from a number to the expression of E equal to IH cross dou by dou t? Because I am seeing the things at a very, very quantum level. I am just going according to that. I'm not just behaving or writing equation as per my wish. No, like that, not like that. So depending on the situation, I'm just converting the systems. Okay, right? So, okay, so there's a question about whether all the theory is applicable to different qubit technology. Of course, whenever you are talking at a tiny quantum level, whatever theory I'm writing, it is all applicable. Is that experimentally proved? Yes, it is proved. All the IBM quantum chips, they're talking about multi-qubits interacting. The way they're interacting, if you want to understand, you have to use this theory. Okay, right? So is that experimental proof? Yeah, long back then people have done these experiments and they have showed it. Whatever the theory was proposed by quantum physics in terms of this, it is proven. Okay, right? Yeah, we are come to that. Why did we do all these things? Why did we do the quantum level of understanding? We want to understand the state of the light. That is the main objective of entire session. Okay, I can just simply give the quantum state of a system of a light is a photon which is vibrating. A photon is a vibrating thing. So I give a Hamiltonian which is represented by half, sorry, h omega n number plus half. This is a Hamiltonian corresponding to your light. If I just simply give you, you don't accept it. You know, I don't see something vibrating in light. I see only photon. How can you write this? And how can you can ask me a question? So n refers to the number of photons in a given light mode. Okay, so this is a complicated answer. I just give, I'll make a PPT and a project. This is the state of the light. This is a Hamiltonian. This is the state of light. If I give you, nobody is going to understand at the initial level unless if you have the understanding of if there is a quantum system, if it vibrates, it oscillates, it is represented by a Hamiltonian. That Hamiltonian is a very complicated thing. To make it more simple, I introduce a like a non-Hermitian operators, a dagger, and now the moment I do it, the Hamiltonian becomes very simple. Now you see, Hamiltonian could be a matrix now. I find the eigenvalues and eigenvectors of this Hamiltonian. From there, I get the insights about the system. From there, I'll know about the system. Okay. Yes. Answer to the question raised by Bhavanaji. That is like even for photons, it is applicable. Yes, it is applicable. Even then, the photons doesn't have a mass. This is a very interesting question. Why? See, people say photons doesn't have mass. How can they have linear momentum? How can they have momentum? Momentum means what for me? Mass into velocity. Okay, remember, but photons have a energy. What is that? Energy is half mv square. It's just like mc square. If something having an energy, I divided that energy by mass, I am getting a unit of momentum. So that is what they do. Take the energy of the photon, divide it by some mass which would correspond to the photon energy, if at all. So from there you can derive the energy, the momentum of the photon. You know why photon has a momentum? You know why? Okay, right? If I just take caroms, right? If you have a carom, if something a pawn is there, if you hit with another pawn, this pawn will deviate, this pawn will deviate in some other fashion. Okay, they do head-on collision, they do deviate. Okay, when they deviate, the momentum of this incoming, the energy of this incoming pawn transfer to that. So the momentum is conserved. You people say in inelastic collision means they are nicely strong. There is no loss of energy in the form of heat or anything. Only energy information or the energy transfer from one object to other object intact. So this is called inelastic collision. So here, so one deviates with a less momentum, other one acquires that reduced momentum and just deviate. That is what we see in the snooker or in the caroms. Or you hit something with a marble while playing, you see that the marble which is stable acquires some momentum and takes some linear momentum and it just travels. The one which is hit got reduced its linear momentum. So the momentum got transferred. Okay. Now, photon doesn't have a mass. It has energy. Now what you do, you hit the photon, okay, with some very tiny electron kind of a particle. Okay, photon comes and hits it, it just deviates. The electron just deviates. You see now, photon is acting like a small tiny particle. And moreover, the duality, sometime back people gave, the waves also behaves like a particle, not just like a wave nature, they also shows a particle nature. Why? Because if I just take a very fine light, very fine thin film, so thin that one atom is there in one layer, if you take that kind of a film, hit with a light, you know, the film gets flickers, just like air is hitting it, even though you do the experiment within vacuum. So this is confirms that photons have a particle nature. Photons have a momentum. Okay, so even though they don't have mass, they do have a momentum. You can calculate it. So just a few simple classical quantum calculations for you, relativity calculation for you. You can check on that. Okay, now we have seen at quantum level things can become so fuzzy. I don't see what is particle, what is wave, but they can show both properties. Now, when it comes to the light, let me use my hand notes now because it is taking too much time. I have to give a break also. I have to give a break here. I'm sorry. Okay, where did we stop? Yeah, this is where we stopped yesterday. Now you see, Maxwell's equations are there. They dictate the system. And I find a wave equation from the Maxwell's equation. Okay, wave equation means what? It describes some disturbance traveling. So there is a wave equation for electric field. There is a wave equation for magnetic field. Now, interestingly, if I have to write down total energy of this wave, electromagnetic wave, it consisting of energy stored in terms of electric field, energy stored in terms of magnetic field. So there is a something called a Poynting vector. From the Poynting vector, you can write the total energy in terms of electric field square in terms of magnetic field square. This is just a simple electromagnetostatics for you, right? So not even quantum, this simple electromagnetic statics, it is there before 1900, before the birth of quantumness. Now if you see this electric field and magnetic field coming in the total energy, now the moment I used earlier conversion, you remember back, I used a momentum into the simplest form and position into simplest form. If you introduce those conversion, what I see, total energy of this electromagnetic field becoming just like electrons electromagnetic energy in terms of p square and q square. And now if you introduce the non-Hermitian operator A and A dagger conversion, you see interestingly electromagnetic field is also having Hamiltonian just like electrons Hamiltonian, quantum particles Hamiltonian. Okay, see, this is no difference, everything is same. So photon is like a particle, smallest particle for me at quantum level coming from the zone of waves. Electron is the smallest particle coming from the zone of material. Both behave like a same in terms of having material property, in terms of wave property. So the Hamiltonian is appearing here. Now from now on, if you appreciate the photon is like a particle whose Hamiltonian just like a Hamiltonian of the electron, then everything becomes straightforward. So you can understand, right? What else can become? I don't have a single photon, I have multiple photons. And from there, what else I can understand? Okay, I'm not talking about a single electron in the system. There are like huge Avogadro number of electrons in the system. How they are going to be understood? So that we another story. But same story here in the electron state as a photon state. We'll understand a little bit more after the 5-minute break. I'll just project this slide. You just have a look at it. Okay, we'll continue after 5 minutes. Yeah. I'll start answering the last question.